All right, guys, in this video, we're going to explore a couple of things. Now, we've already talked a lot about the kinematic equations, how to use them, but you might now be wondering, where they come from? Roll the intro. Do you feel the vibes? We're going to focus on 4 different variables. The first one is going to be x. This one is your position. So think about this as if, wondering where you are in space. V is your velocity and A is acceleration. We're also going to look at time. So we've got position, which is where you are in space, velocity, which is how fast you're traveling, and acceleration, which is how fast your velocity is changing. We also have time. Time is, at what time something's happening. We're going to look at position first. Position is just going to be some value, x. If I want to figure out how fast my x is changing in time, I would take dx dt. This gives me my velocity. And if I want to figure out how fast my velocity is changing in time, well, I would take dv dt, or the derivative of the velocity, which would give me my acceleration. Keep in mind, this is also equal to the second derivative of the position with respect to time. So this is how these 3 variables relate to one another. Now, what we're going to do is we're going to formulate equations for these called the kinematic equations that have one fundamental assumption. That assumption is that A is constant. That means A does not change in time. So we do not have a derivative of A. The derivative of A is 0. So we can start with A equal A. This is my fundamental assumption, where this is the derivative of the velocity with respect to time, and this is a constant. So even though they look like they're the same thing, they're actually not. So now I'm going to replace A with dv dt and keep this A because that's just a constant value. So now that I have that, I can just do dv equals A dt and take the integral both sides. Right, and this would have to go from time equals 0 to some time t. And this would have to go from some velocity, v0, to some final velocity, final t. So now I'm going to get v final minus v initial is equal to, well, at. And so now I get my first kinematic equation, vf equals v naught plus at. So this is our first kinematic equation. Now, I already told you that dx dt is equal to v. So we're going to do the exact same thing. We're going to use this as our v final, in this case, equals v naught plus at, because v final is whatever our final position will be. So we'll end up with a final position here. So when we do the derivative. So we'll get dx equals v naught plus at dt. And then I'm going to integrate both sides. This side, I'm going to integrate from x naught to x final. And this side, I'm going to integrate from 0 to t. So now I end up with x final minus x initial equals v naught t plus 1/2 at squared. So now I get, if I move this x naught over to the other side, x final is equal to x naught plus v naught t plus 1/2 at squared. This is my second kinematic equation. So I now have a way to describe the position and a way to describe the velocity of a moving object. The main problem, though, is that I have the equations to figure out position and velocity, but both of them are completely and totally based on time. So what can I do to figure out an equation that's not based on time? Well, we're going to have v final equals v initial plus at, and x final equals x initial plus v naught t plus 1/2 at squared. So these are my 2 kinematic equations that I have already. This is number 1 and number 2. And now what I'm going to do is plug them in to the other one. So I can solve the top one, number 1, for t, and get that v final minus v initial divided by a is equal to t. And then I can plug that in to my second kinematic equation. Get x final is equal to x initial plus v naught. Well, I have a t there, so it's v final minus v naught over a. And then plus 1/2 a t squared. So v final squared minus 2 v final v initial plus v initial squared all over a squared. So now I can cancel this a out with one of these a's. So So that's helpful. I'm going to move my x naught over to the other side, get x final minus x initial equals, I'm going to distribute this v naught vf over a minus v naught squared over a plus 1/2 vf squared over a minus 2 v naught vf over a plus v naught squared over a. And now I can distribute the 1/2. So when I distribute the 1/2, we'll notice something interesting pops out. I'm going to factor out the a here. So I'm going to get x final minus x initial is equal to 1 over a. So that just takes an a out the bottom of everything. V naught vf minus v naught squared plus vf squared over 2 minus v naught vf plus v naught squared over 2. So now we can see that this v naught vf and this v naught vf cancel each other out. And I'll notice that I'll be left with a 1 over a vf squared over 2 minus v naught squared over 2. So I can then factor out that 1/2 and get a 1 over 2a vf minus v naught, both of them squared. Then this will equal my change in x, or x final minus x initial. And I can multiply both sides by 2a, and I'll get vf squared is equal to v naught squared plus 2a delta x. And this is my third kinematic equation. So this one doesn't involve time at all and is the position based on the acceleration, the initial and final velocities. So if you're solving a problem or anything like that that doesn't include time, this is probably the one that you're going to use. Let's do a small recap. We have our first kinematic equation, v final equals v initial plus at. Our second kinematic equation, which is x final equals x initial plus v naught t plus 1/2 a t squared. And our third kinematic equation, which is vf squared equals v naught squared plus 2a delta x. Now, this is great, and it's really nice to know where stuff comes from. But really the important part of this derivation is the algebraic manipulation of our variables and what they mean. Right? So that can help us better understand where these equations come from to better understand what their limitations are, like a constant acceleration. So now that we've gone through where these equations come from, how to use them, we're going to go into something a little bit more complex. We're going to start adding a bunch of different directions to it. So stay tuned for our next video on vectors, where we're going to learn all about direction. As always, don't forget to like, comment, and subscribe.